Welcome everybody to today's research seminar presented by Protocol Labs. Today we're joined by Shahar Papini from StarkWare, who will present his research titled Cairo, a Turing-complete STARK-friendly CPU architecture. Shahar studied computer science, mathematics, and physics at Technion, the Israeli Institute of Technology, where he graduated summa cum laude. Shahar has won multiple prizes in math and programming competitions, including a first prize at the ACM International Collegiate Programming Contest, a first prize at the Internet Measurement Conference, and a second prize at the International Olympiad in Informatics. So with that, Shahar, I'll let you take it from here and present your research. Thank you so much for joining us today.
Thank you very much for that introduction. Sure. So, okay, I'm talking about Cairo. Now, what is Cairo? First of all, Cairo is a CPU architecture. Now, there's a question of why do we need another CPU architecture like x86 or other stuff? Well, this CPU architecture is not meant to be run on physical hardware or to be efficient on physical hardware. It's meant to be efficient for proof systems, specifically for the Stark proof system, which I'll get into in a sec. Cairo is a joint work by me, Lior Goldberg, and Michael Ryabzev. It's already used today. It's in production in a lot of rollups and StarkNet. It's very practical and very efficient. When people say Cairo, if you hear about it in the crypto world, it's not just CPU architecture, it's also a high-level language and maybe other stuff. But in this talk, I'm focusing on the CPU architecture. The Cairo architecture existed before the said paper we released a few months ago. The new information of the paper is actually all the architecture details and the design decisions and how we do our constraint, which I'll explain what it means in a second. If you want to see the paper, it's written down here. So I'll start a bit about a background. What is the Stark proof system, which we are going to use? Because Cairo is designed to be efficiently provable on the Stark proof systems. So I'll just explain a bit what this means. A proof system has two sides. It has a prover side and a verifier side. And the prover wants to prove some statement, which could be something like, hey, I ran this computation, and this is what I got in the end. And maybe I don't reveal some of the inputs, private inputs, but it talks about some computation. For that, okay, there is some protocol between the prover and the verifier. And in the end, the verifier should say yes or no. And if this proof system is sound and complete, then if the statement is true, the prover can generate something, but the verifier will say yes. And if it's not true, then the verifier will always say no. Now, Stark specifically is also a non-interactive and probabilistic, which means okay, non-interactive means this protocol is just prover generating some data, this proof, and then sends it to verifier and never talks to him again. So the proof is summarized in some chunk of data. And it's probabilistic in the sense that the verifier only needs to succeed with high probability to distinguish. How efficient is Stark? The prover time in memory is quasi-linear in the size of the computation. So we do have some overhead, obviously, to make a proof of a computation, but it's only n log n. The benefit we get by doing this extra work is that the verifier time is sublinear. It's in the order of log squared n, the proof length and the verifier time. Now, just to give some baseline, now there is a very easy proof system that is just here are the inputs, and the verifier can just run the computation by itself. The prover time is like maybe O of 1 or O of n, depends how you look at it, and the verifier time is linear. Right? But in Stark, we want to save this verifier time. We want to make it sublinear. That is why we are doing this. Another nice property of Stark, it's transparent. It's a security thing. That means we don't need to. Other proof systems have some sort of ceremony at the beginning, which people can sometimes cheat. Well, this doesn't have all this computation. This security relies only on hashes. basically. So it's also post-quantum secure, if that's interesting. And the thing we will dive into in a minute is how I will present this computation, this statement for the Stark system. We present it in something called AIR, which is an arithmetic intermediate representation. It's basically a bunch of polynomials. And AIR looks like a pair of trace and constraints. The trace is a big table of field elements. We use prime field element in Cairo. The trace has a few columns and a power of 2 of rows, which the number of rows is usually a lot larger than the number of columns. And together with this trace, we have constraints on this trace, periodic constraints. For example, okay, the constraint should be polynomial of low degree. The lower the degree, the better. And the constraints can repeat every power of 2. For example, this says that xi squared minus y at I plus 2 is 0. But it happens here and here. It jumps of 2, maybe. This can happen jump of 8. So basically, we have repetitive constraints. They are polynomial. We want them to be small, if possible, not very big, because the verifier is paying for it, and of as low degree as we can. For example, 2. Now, specifically for Cairo, I'll show you at the end. We will achieve degree 2, and not a lot of constraints. It will be pretty simple. But this is the general way we prove computations in AIR. When we will talk about Cairo, basically, we will create a specific AIR, and the trace here will represent a computation on this CPU architecture. So you can think about, I have a few columns which maybe have the values of the register at a specific point of time, and maybe some memory accesses, and every row is the next computation step. And the constraint will verify some consistency, for example, that the register value is the same unless something happened or it's some opcode. So this is a general picture you should have in your head. Each row is a specific computation step on this architecture. So first of all, why do we even need Cairo? Before we had Cairo, we actually needed to create an AIR, an algebraic representation for every problem we need to solve. For example, if we, as StarkWare, wanted to solve to represent the statement of a decentralized exchange, for example, then every row could be some transaction, maybe deposit, transfer between 2 accounts, something like this, and then we need to manually write the constraints and how they operate. Doing this for every new problem is a tedious and hard process, so we'd rather not do it if possible. Another issue with it is that it's repetitive in its nature. So if I have some computation I want to do that is not repetitive, maybe it has 2 parts, maybe the first part does all the transaction, the second part is doing some compression or something on or some complex logic, then it's very hard to present it in something like this, because it's just sort of a repetitive thing. So presenting programs with complex logic is very difficult here. That is another reason we want this. Another benefit of having Cairo is that we'll have only a single error. So instead of having to make an error for every new problem, we will just make one error. And this error will verify execution on this abstract machine, this Cairo architecture. So and then we'll need every new problem we have, we'll just need to represent it in the CPU architecture, and then just prove the execution of the CPU architecture, which has a single error, like I said, a universal machine. And another thing we want from this CPU architecture is that it will be efficient in the sense that the trace will be as small as possible, the constraints will be as small as possible, because these are the main costs of the Stark protocol. Like I said, the proving time is quasi-linear in n, which n is basically the number of cells you see here, the size of computation. So if you have less cells, the prover is more efficient, and so is the verifier. So yeah, when designing a Cairo, one of the main things we had in mind is how to make it as efficient as possible. So the first thing we need to tackle is the memory model in this CPU architecture. I'd say the classic memory model of a von Neumann machine is just a read-write memory. You can set values at some addresses, you can read values, and things like that. Well, this is not very efficient to write, and I'll dive into it right now. But first, we need to understand what actually is the problem we're trying to solve this memory model, how we can represent it in our AIR, in our arithmetic representation. So basically, we probably, in this trace, in this table of field elements, at each row, we might have some accesses. The access could be like a column saying, this is the address, a column saying this is the value, and a column saying this is the operation, maybe it's a read, maybe it's a write, something like this. So imagine that every row has this triplet, and we need to use some polynomial constraints to prove consistency of this memory. What does consistency mean in this regard? It means that if I write a value at address 5, the next read on this address should be the value I just written. Like if I wrote at this address 100 and I read 200, it's not consistent. So we need to prove the consistency of the writes and the reads on this memory. Now, the first problem we encounter is that these constraints are non-local. And this doesn't really fit with how we do constraints in AIR. Remember, our constraints are some polynomial with like a constant offsets here, like y and y plus 2. It's not y and y I plus x or something like this. Just constant mask, I would say, constant offsets, and it's repetitive, repeating every time. So doing some non-local constraints on the next time I read it with this address, this is something that is not trivial how to do, but we can solve it. And the way we solve it is using a permutation trick, I'd say. Imagine we had some primitive that can sort all the accesses according to something. So then what we would do is take all these accesses, we'll sort them by address, and after address, we'll sort them by time of access, the step number, and then the constraints become local. No, I only need to check maybe this access and the next access at this address. So it will be sorted, so they will be right next to each other at the trace. I'll repeat how it looks like. Imagine that we have some 3 columns, like address, value, and operation, which represent the accesses in the chronological order. And we have another 3 columns, which are called sorted address, sorted value, sorted operation, which are the same triplets, only sorted by address and time. And then the constraints could be on these sorted columns. And now I still need to explain to you how we sort and how we write these constraints. Well, doing these constraints for the read-write memory is kind of expensive. We need to verify that this new column is indeed sorted, which will be most of the cost. And okay, it's mostly on the sorting thing that is a problem. And we need to verify also that if I have a write, then the next one is read, and the address is the same, then I need to make sure that the value are the same. And this comes down to, like, I need to add a bit more temporary self. This it's just some details, but it's not the most efficient thing in the world. The memory model we chose, which I will show you the exact constraints for it in a minute, and then you'll understand better, is something you probably won't see in a regular physical CPU architecture. This memory model is, first of all, it's read-only, which is weird. How can you program with read-only memory? Which you can program with it because it's non-deterministic. And I'll explain in a second what it means. And also it's continuous. Continuous means that the set of addresses I access is a continuous range, 0, 1, 2, 3, 4, etc. These properties in the memory model lets us verify memory with only 5 trace cells. These 5 trace cells are the address and value, the sorted address, sorted value, and an extra trace cell, extra column, actually, which I'll show you in a minute. But 5 trace cells is pretty good. Like the respective read-write memory would probably be depends on the address space, but maybe 30, 40, maybe something like this. It's a lot more expensive. Okay, so now a bit of math and how we verify this, and then I'll show you how to program with read-only memory, which is nice. But first of all, how do you verify that this is consistent memory? Now, for this model, because it's read-only, I actually just need to verify that this is a mathematical function. That means that if I have 2 rows with the same address, then they need to have the same value. And so what I do, first of all, is how can I sort these triplets or pairs in our case, because read-only memory doesn't have the operation column. So I need to sort these pairs. And for that, we use the permutation trick. What is the permutation trick? Basically, okay, imagine I have this set of pairs, AI, VI, and another set of pairs, A prime I and V prime I. And I want to show that these 2 multisets of pairs are the same. Well, if I consider this polynomial, in the variables Z and W, in the left side and the right side, same polynomial in Z and W. And this is product on all the elements of this multiset. So this multiset equals the right multiset if and only if this equation holds. Because these actually represent the roots of this polynomial. For example, as a polynomial in Z, these are the roots. And the polynomial, if it's monic, it's represented by its multiset, set of roots. So we know now that we can use this polynomial if this polynomial equals this polynomial, that it's the same multiset. But how can we compute this, verify this in an error? Well, the trick is not to verify it as a polynomial, but to do inequality testing by choosing a random value for Z and W. Once we chose a random value for Z and W, then we need to calculate this single field element from the left and single field element from the right. And if they're equal, then with high probability, the polynomials were equal. And this is easier to do in error. what we are doing is adding a new cell, which represents the cumulative product until some number. So at the first row in the array, it will be just z minus a0 minus wv0. The next, and then we have constraints that says that the next cell is a previous cell multiplied by this thing. So this constraint will make sure that this entire column is a cumulative product of these things. And in another column, we'll do on these values the same thing. And then we will need to add another constraint at the end that the last row, this column equals this column on the last row. And using this cumulative product trick, the permutation trick, we can verify that with high probability, the multiset of AV is the same as the multiset of A tag A prime V prime. Okay, so this is a permutation trick. But we also need to verify that the new A prime V prime are sorted by address. And here we use the fact that the memory is continuous, which means that if I look at the pair of addresses, either they are the same address or the difference is 1. And this is the continuity and I'd say a sorting constraint, this thing. It's of degree 2, which is nice. We wanted low degree. So the difference in address is either 0 or 1. And the next constraint we want to check for is that if these addresses were different, then okay, if these addresses were the same, then the values are the same. Now, because we already know that the difference between the addresses is either 0 or 1, then we could say, no, either it's 1, which we don't care about the values because they're different, or it's not 1, so it must be 0, and thus we want the difference in values to be 0. So either this is 0 or this is 0. This is a single valued constraint. So overall, this requires 5 cells, 2 for A and V, which we'd need anyway, 2 for A prime and V prime, and 1 for this cumulative product. Like as I described it, we needed 2, 1 for the right side, 1 for the left side, but we can save it because we can divide. Just to compare it to the read-write memory, if you have read-write, this constraint will be a lot more difficult, and this will be a lot more difficult too. In here, the address might have been very far apart, and a single value we have to account for the operation. We need to use some range checks if it's far apart, which is a complex, a more complicated primitive that says the difference between two values is not very big. It's not that trivial to do it in polynomial constraints. It requires extra cells that represent the bits. So it's more expensive. Okay, I'll wrap up this bit about the array. It was kind of technical and very related to how we create polynomial constraints for Cairo. This is an example of the considerations and I'd say the process and what actually Cairo is in its in the bottom level. This memory model is probably the first thing people ask us why we chose this weird memory model. And it's very efficient. And it looks like this. The paper describes more. So, okay, after we went past through this math stuff, and I just want to say why programming in read-only memory is easy. We have a read-only memory, but it's also non-deterministic, which means that as long as we didn't touch a memory cell from the beginning of the program, we don't really know what's there. The prover can choose what is there. Why is that? Okay, imagine we have this, basically with this trace, okay, we just have constraints, and the prover is starting to create this trace. This is the next instruction, I run it, this is the next instruction, this is the next instruction. But the prover, when he is generating this trace, he doesn't know the values of the memory. He says, I'll think about what I set them for later. And at the first time we access some address, then the memory, the prover can say, actually, I want this memory address to be this. Okay, this should be the value of the memory, and so it behaves like write once memory. This non-deterministic read-only, essentially a write once memory, because the prover, the first time he sees this any access to a specific address, he can pretend that this was the value all along. This means it's basically a write once memory, and we have programming languages or programming models that use immutable memory, which are called functional programming, functional style programming. So everything that is read in Cairo today is using that. It's all immutable memory. You actually don't need more than that in order to be Turing-complete. One thing to note is that we don't have any loops, because loops require some iterator that we need to change its value. We can't, our memory is immutable. We can only write to it once, so we can't change iterators. But instead we have recursion, like functional programming. The recursion, we can do recursion because we do have 3 registers actually that are kind of immutable. The entire memory is immutable, but we have 3 registers that in which FP represents the current frame pointer, which is basically the stack. So we can, when we want to call a function, we allocate new memory and we make FP point to it, and this is like pushing the stack, and we can pop from stack by changing FP. So by only using 3 registers which are changeable, we can do calls and recursion and have everything we need. It's also nice to have an immutable memory in regards to security. I mean, we had a lot of instances where programming in conventional model would have been dangerous, but when you know it's immutable, you don't have any problems. One of the things we can do is just call unsafe code that you got from someone you don't trust. In Cairo, you can run it, and you're guaranteed that if the proof passes, then it didn't mess with your program, which is a very nice benefit to this memory model. So registers. Registers is also a design choice we did that is different from physical CPUs. Usually physical CPUs have a lot of registers because they're cheap and to hold, cheap to operate on. And in this case, it's not so. First of all, memory is cheap, not like physical computers, because memory only uses 5 trace cells. A register needs at least 1. And the Cairo overall has 5 cells out of 50 is not a lot. But registers do have additional costs. They add verifier cost. Why is that? Imagine I have 20 registers and I have some opcode that needs to operate on one of these registers. Then I need to have some multiplexer, some way to choose between these 20 registers, which will mean we have a constraint of size 20, some polynomial constraint with 20 coefficients, something like that. That would have a cost in the side of the verifier, because all the constraints are something that the verifier needs to compute. which we don't want. We want the constraint to be small. And also, modern CPUs have a lot of registers. If we use memory instead of registers, we can basically have infinite registers. So instead of paying 20 cells for each step, which we don't use all 20, probably only use but 1 or 2 registers each opcode, and we don't want to pay for the ones we don't use. Instead, we do only memory. And in Cairo, we have 4 memory units per instruction. And these memory units can access like 2 to the 16 memory addresses, like relative to where you are right now, which basically gives you 2 to the 16 registers. And you don't pay for all of this. You just pay for the ones you use for these 4 access units. So it's 20 tray cells for 4 accesses that lets you access a lot of so-called memory registers, I see. But we still need some registers. We have the PC, which is program counter. It's very basic where we run right now. We have 2 more, allocation pointer and frame pointer. Now, because the memory model is write once, the way we program is we basically have this AP, allocation pointer, which means all the values, all the addresses from 0 to AP are already allocated. Someone is owning them, but all the addresses from AP and beyond are free. You can allocate stuff on them. This is AP, allocation pointer. FP is, like I said, the frame pointer. You can think of it as the pointer to where the locals and arguments of the current function are at. And when you call another function, you basically allocate things, allocate the new frame, point FP to it, and when you return, you return to the previous one. So just 3 registers, and this is everything we need. The next design choice we did differently is about decoding instructions. How does decoding instructions usually work in physical CPUs? Usually we have some lookup tables. For example, we have opcodes which are represented by at least 1 byte, and we have some table that maps from this byte to a set of flags in a way. And these flags tell different components inside the CPU what they need to do. For example, the ALU would have flags if it needs to add or multiply or divide, do something else. The memory will have control flags that tell him to read or to write. So across the CPU, you have some flags, and the decoding takes this opcode and looks up these flags. Now, lookup tables are more expensive in polynomials. Bit manipulations are very expensive as well. Don't want to do bit manipulations. Instead, what we do is directly have the control flags as the opcode itself, instead of doing lookup tables. And we use range checks to decompose. Now, what does this mean? This means that if I collect all the flags from all the parts of the CPU and I concatenate them, then I get some representation. This will be the representation of the opcode in this system. This basically, it means we don't need to do any lookup because it's just the value. It's like the ID function in a way. We do need to decompose it to bits. Don't need to pull different bits, just need to decompose everything. The downside is that we don't want a lot of bits, a lot of flags. So we need to be more compact in our control flags because it costs an extra cell trace for each flag we have.
There's a question here for you. And it says, do you have a read-only stack and a read-only heap?
Basically, yes. We have the read-only. Okay, the stack is not read-only. It's a immutable stack, but it's implemented on top of this immutable memory. Now, if you are familiar with the persistent data structure or immutable data structures, basically, think of it as a linked list. A linked list. When I want to push to this so-called stack linked list, I find an empty memory. I take this empty memory and I write the value of the stack, and then I add a pointer to the previous head. This is a push. It's a push on a stack, but implemented on top of the immutable memory. And I can also do a pop, just make the FP point to the previous head, to where I point to. So we can have a linked list, and this gives us a stack, immutable stack on top of an immutable memory. And we also have a heap in a sense. And first of all, notice that you don't really need a heap because we can just take, if you need to allocate 100 words, you can take AP to until AP plus 100. This should be a new untouched memory. And then you advance AP by 100. So you just got yourself some 100 empty cells in the memory. But we also have some other tricks because of non-determinism of Cairo. You can basically guess an address somewhere and use it as an unallocated memory, which is it's more in the nature of the non-determinism of Cairo, which is very interesting, but I have not touched. So you can have heap and you can have a stack in a pretty straightforward way, even though the memory is immutable. Whereas the instructions are basically concatenation of the control flags, and we concatenate offsets as well. Today in Cairo we have 15 flags, I believe, 15 flags, each is a bit, and it's enough for all the parts of the CPU. I have a nice picture in the end, maybe I'll show you if I get there. Another downside of having this, it means that we have some undefined opcodes. Now, if we had this lookup table, then we could control exactly the set of flags that are possible. Maybe we don't want to have the multiplication flag on together with the addition flag. So we won't have it in a table, but in this representation, we don't have this lookup table, that you can play with all the bits pretty much, and have some combination that don't make any sense and could do weird stuff. So we might have undefined opcodes, but it's okay. Doesn't matter for us. You know, if you want to represent some statement, we will represent it with a set of opcodes, you know. This is how the decoding constraint looks like. Basically, we have this memory value, which is a value we just read from memory. If you remember the memory units, this is just the trace of one unit. It's also already verified that this is indeed the value fetched at PC. So this is your trust. And this constraint is used to fill or to deduce all these values. Now, what are these? These are the flags. You can see to the right, F0, F1, blah, blah, blah. Each one is bit checked, which means we have a constraint that it's either 0 or 1. So this is basically bits, decoding to bits. And these are offsets. We have 3 offsets, which represent, as you remember before, the kind of memory register. For example, if we want to do some operation, a possible operation is to take the memory cell at FP plus 1, say it needs to be equal to FP minus 100 plus the value at FP minus 200. So these 3 values we have in this instruction, we have 3 values are these 3 offsets we have here, 1, 2, 3, and there are 16 bits represented by minus 2 to the 15 until 2 to the 15. So you can access below and above. This is what we have a teacher instruction.
There's another question here that says, as I understand, the prover doesn't transmit the memory trace. How does input-output work? Say input of n and output of m elements, considering the program as input.
It's a good question. This is the public memory, like in 2 slides. I skipped to this public memory to answer this question. Yeah, basically how, okay, like you said, the prover doesn't show the entire trace. It just shows, hey, I have an assignment to the trace that makes all constraints valid. This is basically what it says. So in order to output some data or have some input, we need to have some constraint, basically, that says, hey, maybe this cell is 5, value 5. And if this is a statement that both the verifier and prover agree on, the verifier knows, hey, this cell is 5. So basically, this is how we transform data outside of Stark proof. And what we do in Cairo is kind of tricky. Which value do I? Let's go back to the memory model. If you remember, the way we did the memory is saying that this product equals this product. Basically, it's not true. This is not the constraint we have. We have here times C. What is the C? C will come from outside and represent part of the memory that is not inside this trace. Basically, think we are not sorting these original columns. We are sorting the original columns union some columns that we don't see, but we know that the product on them is some number 15, and the verifier can also see the 15, and the verifier can compute by itself this part of the memory it needs. Another option would have been just to maybe hash the values. Now, if I wanted to output something out, compute the hash of these values, and then have it in a single trace cell, and the verifier would have a constraint in this and output this single value, which is the hash. This is enough to output as much data as you want. This public memory is just an optimization on this process. It's sort of an algebraic hash in a sense. You can read more details in the paper, but just to for efficiency, it's pretty efficient.
There is a follow-up question with you here that says, so the verifier cost scales with the size of the input output.
This is by definition.
Okay.
If the verifier wants to maybe verify that the output is these 100 words, then you will have 100 words that he needs to do something with. If he just wants to verify that maybe the hash is something, we can just output the hash. You should output exactly what you want the verifier to go over and see. The verifier is linear in the size of the public output you have. But again, you can output exactly what you want the verifier to go over. The problem with doing the hash is that currently we don't have any hash that is both Stark friendly and Ethereum friendly. Ethereum is where we have our verifier on the blockchain on Ethereum. Ethereum usually uses Ketchuk, which is very expensive on Stark, and Stark uses Pedersen, which is very expensive on Ethereum. So that is a problem. If we had a hash that is friendly for both, we'd probably use it over the streak. But the streak is nice and efficient. And this is what I said before. The product actually has time C somewhere, and this C is known both to the prover and the verifier. And it's important to make sure that that is derived randomly after the portion of the memory that is public memory, and public addresses, public values. So it's a trick. Okay, I didn't want to dive too much into public memory. If you want, you can check the paper or just ask me questions later. But it's not a thing that I do want to talk about is the built-ins. I said Cairo is Turing complete. but it doesn't mean that everything is efficient, even though it's possible. For example, computing hashes might be an expensive operation. We want to do it a lot in most applications. So instead of doing everything in pure Cairo, we have this concept of hardware, or we call it built-ins, which are specific errors written for a specific task, which exist in the trace alongside our Cairo error. Imagine we have two errors, one for the Cairo, one for the hash, and they live together in the same big trace. And the way they communicate is through memory. Cairo has memory units, and for the special hardware error, for example, for the hash error, we also add memory units on top of it. And every time, every instance that has this input and this output, then it is also written to the memory. And at the end, this memory is united. So these memories live in the same memory space. So basically, this is how we talk to all our built-ins to memory. It's pretty efficient. The alternative of maybe adding specific opcodes for hashing, things like that, are wasteful and expensive. First of all, we don't want the hardware to repeat like every 2 steps or every 4 steps, because you would not use most of them if it's like this. You can't predict where in the program you will use hashes, and trying to synchronize it with the program is a bit weird. So instead, they are synchronized using memory. For example, if the program used only 1,024 hashes, even though they used it mostly in the end of the program, 1,000 hashes could be the error for this hardware could be spread equally in period of power of 2, which is nice for the constraints. They are periodic in power of 2, and the memory units would maybe the address space of will be spread, and even though they are in different places, because they talk through memory, then it will be okay. This also allows for a flexible layout. Like I said, we don't have to choose the number of hash instances before the program ran, in a sense. You can say, run the program in our brains and say, it uses 1,000 hashes, so add 1,000 instances of this hash in my air and use them. So I don't waste, like I don't use more than twice the number of hashes I need. I say twice because we also always need to be power of 2 because of the way stocks work. So it's also efficient in how many instances we have. And yeah, web memory units. So, we have a lot of built-ins for hashes, signature verifications. The output is also okay. Final words about Cairo. They agree to, like I said, which is great. About 50 trace cells per instruction, which is also pretty efficient. And built-ins are mostly dominant in most applications, which means that we almost get the efficiency we would have gotten from a handwritten error. Like a handwritten error is I'd say the analogy of an ASIC, where Cairo is the analogy of a CPU. So if you have a CPU, but most of the things it uses are hashes, and hashes have an ASIC for them, a hardware for them, then your program will be very fast. This is the same concept. If most of the things we're using are hashes or built-ins, then it will be mostly bound by the hashes and pretty efficient, because you'd also get the benefit of the logic in Cairo, the flexibility in writing logic in Cairo, but the dominant cost would be from the handwritten error of the built-in. I think I talked about everything I wanted to talk about.
Looks like we do have one that it says, how much does one trace cell cost?
The numbers vary.
Snark specifically, it looks like.
For Snark, well, we are doing Starks, not the Snarks. Yeah. The question is how many trace cells we can do at how many times, how many costs. I think these numbers are can tell you roughly, millions, maybe billions of trace cells, but no, I can't really get into the specifics because it's dynamic and changing, depends on the efficiency of the prover, and reveal some information. But yeah, on the order of millions to billions.
All right, everybody. Thank you so much for coming to today's talk. Thank you again, Shahar, for sharing your very interesting research. I know we had a lot of good Q&A during the session. If anyone is curious as to further talks that we have upcoming and would like to stay more involved in updates happening with protocol research, make sure to follow us on our new Twitter account. It is @ProtoResearch. That is @PROTO Research. Also, make sure to sign up for our mailer in the description below. Click on the link, sign up, and we'll be able to send you information every month about potential new speakers and updates that we're having here at Protocol Labs. And finally, if you're a researcher and you're looking for some grant funding, make sure to go to our website, grants.protocol.ai, to find out all of our grant offerings. So one last thank you, Shahar, for joining us today. Really appreciate it. And we hope you had a good time.
Thank you for having me. Goodbye. Thank you.